Welcome to the session on weighted ensembles. So, automated machine learning provides a candidate pool of models that are already trained. They differ by the algorithms that are used, so the underlying machine learning model, their hyperparameters, the seeds, and also the pre-processing choices. And several candidates often have similar validation scores. But there are also usually a lot of candidates that actually have very different scores and that we want to exclude. Picking one winner can now be brittle when the validation estimates are noisy. You might pick one of the models that look good but might not be as good as they could. And averaging all models together would clearly also include really bad models that we actually want to avoid. So weighting keeps useful candidates and actually controls their influence. So we can see this as a two-stage procedure. AutoML creates the portfolio, and weighting is then a soft model selection where we don't have to restrict ourselves to a single model, but where we can actually reap the benefits of having trained multiple models. So how do we go from equal weighting to weighted average? So equal averaging or equal weighting can be seen as a very simple heuristic where we assume all the models are equally useful. This might be the case if we create them by applying random variations to the data, such as in the backed decision tree or random forest model. However, if we assume that the models stem from a search procedure, we might rather assign different weights to them to make stronger models have a larger influence in the final ensemble. Now, how does this look like mathematically? For classification, if we have probabilities, we multiply the probability vector by a weight per model, and these weights should all be larger than 0 and sum up to 1, so that after averaging the predictions of the different models, we obtain a valid probability distribution for every data point. For regression, the setup is simpler. We can simply multiply the prediction by a weight per model, and technically these do not need to sum up to 1, and technically they also don't have to be larger than 0, so we can also have a negative weight. In practice though, it might be beneficial to also only use positive weights to make the modeling problem more controlled. So now let's visualize the whole process. Assume that we have trained M base models. We learn a weight vector, W1 to Wm, and the final prediction is then a convex combination. And better weights can improve over equal weighting, and we can see here on the right-hand side an illustration of this. Let's have a look at some concrete numbers. Here we denote the balanced accuracy on a 1/3 holdout split on the SONAR dataset. We train the random forest, the KNN model, and the logistic regression. We can see that they vastly differ in their performance. If we were to pick one model, we would probably go for the random forest because it is a good default model that often doesn't require tuning, and that is very robust in a lot of different scenarios. Let's say a lot of different. It's very robust on a lot of different data sets. If we use equal weights, we actually get quite good results already, 0.857. So we improve over using logistic regression and the random forest. If we, however, also tune the weights a bit, we get even better test performance, 0.867, which is quite a bit better than equal weighting. It's important to note that both are not necessarily always better than picking the best model, but the best model is often not known in advance, and thus actually ensembling together multiple models can make sense in practice. So how do we obtain these weights? The weights on the previous slide, I obtained them by manually searching for them. In practice, that's not what we want to do. We want to automate as many parts of machine learning. Thus, we also want to automate the model building. So we seek weights that optimize the estimated generalization performance of the weighted combination as depicted here or as denoted here by this optimization problem. If this is the mean squared error, we can simply use any numerical solver if we also have simplex constraints. That means if we want to constrain the weights to be to sum up to 1, this becomes a quadratic program. If we use non-smooth metrics, for example the 0-1 loss, also known as accuracy, this becomes a hard problem. Typically finding the weights then is an NP-hard problem, so we actually then use some heuristics in order to do so. In practice, these heuristics might be a black box optimization over W. So using, for example, one of the evolutionary algorithms that we have learned about, use greedy ensemble selection, or use stacking with a linear meta model so that we actually learn how to combine these. A downside of this methodology is though that this introduces additional design choices by themselves. So we actually want to pick a method that is rather general and that works really well in practice over a lot of scenarios. To summarize what we've learned in this video, we've seen that weighting acts as a soft model selection over the candidate solutions produced by an AutoML system or hyperparameter optimization tool. Good weights depend on the validation performance and model complementarity, and the weight optimization can improve over equal averaging but adds additional design choices. See you in the next video.